Hi, I'm Alistair. I make escape room games. And when it comes down to it, pretty much all the fantastic interactions you find in escape rooms come down to the same basic technology. Whether you're returning a dragon egg to its nest, placing an ancient relic on a ceremonial altar, or arranging statues in order on a shelf, behind the scenes there's some sort of sensor that detects the object being placed, applies some sort of logic, and then triggers an output based on the result. Now, I've made escape room puzzles using all sorts of sensors. I've used weight sensors, light sensors, touch sensors, magnetic sensors, RFID sensors, and each one of those gives the opportunity for a different sort of interaction, which ultimately makes for a more interesting and varied player experience. Now in this video, I'm going to demonstrate an escape room puzzle using another sort of sensor, which is this inductive sensor. Now, very simply, this is an electronic switch, which allows current to flow through a circuit depending on whether a metallic object is detected in front of it. So let me show you an example of a puzzle where you could use this. Here I've got a table that's been laid out for a meal. And the only thing on the menu is this iron bar, but that is currently securely locked to the maglock on the plate. Now, there's no cutlery bin laid out, but there are silhouettes for where they should be placed. So I'm just going to lay the table. So I've got a fork, which I'm going to put there. I've got a spoon at the back. And then as I place the last item of cutlery, you'll see the maglock releases the bar and I can enjoy my meal. Very high in iron. Now, I should just point out that the sensors I'm using here are unable to differentiate between different metallic objects. So if I just put that back again and let's say I swap the spoon and the knife over, the maglock will still release. So that means that this sensor is not going to be suitable for every scenario, but the great advantage of it is that I've not had to do any modification at all to these items. This is actually my regular household cutlery. This is just stainless steel. You can see I've not had to put any tags or any kind of preparation on them. And they will just work by being detected through the surface here. Now, in order to show you how this works, let me just lift the top off here and show you what is underneath. So you can see I've got my 3 inductive sensors, which I've positioned underneath where the silhouettes on the board were. They are wired to this relay on the back, and that is controlling power to the maglock, which is on the plate. So it's really a very simple circuit, and it doesn't require any programming at all. So let me tell you a little bit more detail about how it works. Inductive sensors work using the principle of electromagnetic induction. So they have a high frequency oscillating circuit that creates a magnetic field. And that magnetic field induces eddy currents in any nearby conductive materials. Those eddy currents then cause a change back in the magnitude or the frequency of the oscillation, and that can be detected by the sensor. So these sensors work best when detecting ferrous metals like iron or steel, but they can also detect most other metals, aluminium, copper, brass, and unlike capacitive sensors, inductive sensors will not be triggered by water or skin. So they're very easy to install. They're simply threaded cylinders, so you can simply drill a hole of the correct diameter in a bit of wood or plastic and push them in. And then you can mount them by fixing the securing nut onto the other side. It's worth mentioning that when you fix them in place, you want to avoid any metallic hardware near them. So I haven't screwed this bit of wood in, I just put some quick dowels into this little assembly here. And obviously because they're not affected by wood or plastic, you could also put a sheet in front of them and they will work through it just fine. Now the sensors come in different sizes. This one is a 28mm diameter and this one is a 12mm diameter. Broadly speaking, the larger the sensor, the greater the distance it will detect metal at. But I found it's not quite as simple as linear distance in front of the sensor because they're also wider surface areas here. It's more the general radius of the area in which an object will be detected. Now, in the context of an escape room, a bigger sensor not only means that you can mount the sensor further away beneath the surface, but it also, players have to be less precise about placing a metallic item directly in line with the sensor, which is generally a good thing as well. Now, the detection range not only depends on the diameter of the sensor, but obviously also the object you're trying to detect, both the type of metal it's made from and the shape of the object. So to demonstrate the effective range you might expect to get from these sensors, let me show you a little experiment. So I've got my two sensors here, and they've both got an LED light on the back of them that will light up when they've been triggered. So if I just point those so those are facing up, hopefully you'll be able to see them. Now if I just find some metallic objects I've got lying around my workshop, so here I've got a spanner, it says it's drop forged steel. If I hold that in front of both sensors, you'll see the LED lights on the reverse there go on for both of them. Now if I bring that slowly in, what you should note is that the large sensor here, the LED has gone off on that much sooner than on the smaller diameter sensor. So that's because this has got a greater reading range. And the distance I'm getting there, what's that distance there? That's about 1.5 centimeters, something like that. It's about my finger width that it is being detected there. What other objects I've got? I've got a screw bit here. And again, you can see I have to get much closer on the smaller diameter sensor there to trigger that off. Also, if I hold it this way around, actually it doesn't make as much difference as I thought it would do. I thought it would detect better in that axis, but actually it's largely the same. I've also got a bag of nuts and bolts, and you see I'm pretty much obtaining the same results in each case, which is that the sensor here is always going to be more sensitive to it. If I get a much smaller item, oh hang on, a hammer, no, about the same again. So it's not going to work for very small precise items. You really want something that's got a reasonable surface area, and ideally that surface area is going to be axis aligned to the sensor. And I would also recommend get the largest sensor you can, because it's unlikely to be so sensitive to be a problem. And if you do that, you can expect to get a detection range of, like I say, just over 1 centimeter probably, and that should be pretty good. Now, to understand how to wire an inductive sensor into a circuit, I think it's easiest to first look at the simple case of where we just have a single sensor. Now, these sensors generally have 3 wires. There's a brown wire, which is the positive power supply, a blue wire, which is the negative power supply, and a black wire, which is the output signal from the sensor. However, there's actually different ways to connect those wires depending on whether you have what's called a PNP or an NPN sensor. Now, functionally, these are completely equivalent. They both allow current to flow through a circuit when a metal object is detected. However, where they differ is the position in which they're placed into the circuit. So a PNP sensor, which is also called a sourcing sensor, switches positive power to the load. You can think of that as the first P here. So in the circuit on the left-hand side here, you'll see that I've got a DC power supply, and the positive lead from that supply goes to the brown wire of the sensor. Now the negative terminal of the DC power supply goes to the blue wire of the sensor. Now, when the sensor detects a metallic object, current is allowed to flow from that positive power supply through the black output wire to the load device you want to control. And in this circuit here, that's depicted by this light bulb. So you can think of this as a high side switch. It's placed into the positive side of the circuit between the load and the power supply. Now, an NPN sensor is a sinking sensor, and that switches the low side of the load, or the negative side, which is the first N again. So it allows current to flow through back to ground. So to wire an NPN sensor, you'd follow the layout I've got here instead. As before, the brown wire of the sensor is wired to positive and the blue wire is connected through to negative of the power supply. However, the black wire now is connected to the negative side of the load. The positive side of the load is already connected to the power supply, but current only passes through it when the sensor detects metal and switches open. So that syncs this black power line here through to ground through this blue wire back to the DC supply. Now let's take a look at how you'd connect multiple sensors in series. Now I'm using NPN sensors, and so this is how you'd wire 3 NPN sensors in a row. If you had more than 3 sensors, you could simply extend this design to incorporate as many as you want. Now once again, we've got our load device depicted by a light bulb, and for this bulb to light up, it needs to have a continuous circuit between the positive and negative terminals of the power supply here. Now, because I'm using NPN low side sensors, the positive side of the bulb is already connected to the positive terminal of the power supply. But to get the negative side connected, it has to pass through all of these sensors first. So imagine how this works. At the outset, it's only this sensor on the right hand side that's actually functional, because that's the only one that has both its brown lead connected to the positive side and also its blue negative lead connected to the negative terminal. That's the only one that's directly placed into the circuit. So when this sensor detects a metallic object and becomes activated, it allows current to be sunk through its black output lead through to its negative lead here. And what that lead is connected to the blue negative terminal of the previous sensor. So the effect of this sensor becoming activated, it means that this sensor now becomes functional because it is now placed in the circuit. It's got its power supply from the positive line in the brown here, and its blue negative side is able to be sunk through the black output of the activated sensor here. And now we do the same thing again. Now if this sensor becomes activated by a metallic object placed in front of it, it allows the blue negative terminal of this one here to be sunk through its black output lead, and we now have a series chain of 3 sensors in a row. We've got this one being sunk through its blue lead into the black one here, which is being sunk through its blue lead into the black terminal here and back to the DC power supply. And it's this final sensor here, the one that's actually closest to the load. When this one becomes activated, that is what then connects the low side of the load device all the way round into this continuous circuit, and that is what makes the lamp come on. Now, one of the downsides of this design is that these sensors actually only become functional in order one at a time. So you can't activate this sensor before this one, let's say, because it doesn't actually have power going through it until this one has switched on first. Now, in practice, in most escape room puzzles, let's say where you have to place 3 items, as I did with my 3 pieces of cutlery, that doesn't matter. If this sensor has its object placed in front of it first, and then this one comes online, what will happen is immediately all 3 of them will become activated and the circuit is closed. However, in certain circumstances, it's nice for a games master to be able to see remotely that this item is placed correctly and this item isn't. And you wouldn't actually be able to achieve this with this particular circuit design. You'd have to design a more complicated parallel circuit instead. But I think for 95% of cases, this design is actually perfectly adequate. So that's how you can use an inductive sensor in an escape room puzzle. And hopefully you found this information useful to be able to add to your arsenal of escape room tech. Now, these sorts of sensors are generally used in industrial applications to detect whether a moving piece of machinery has reached the end of its gantry or something like that. So they're very robust and durable, and a puzzle like this can run 24/7 for years with no additional maintenance. Now, obviously the theme I've chosen is fairly mundane, and maybe you do have an escape room where you have to set a tea party in Wonderland. But maybe you have something a bit more fantastical, a dagger, a valuable necklace or amulet, or an alien artefact. So long as it's an object made of metal or contains some metal components, it will work with these sensors. So I hope you found this video useful. If you'd like to support me to continue making these kind of escape room tutorial projects, please do consider supporting me over on Patreon. I'll put a link in the description below. And if you do already support me on Patreon, thank you so much. I'll be putting a post up shortly containing further resources for you to download. Otherwise, if you've got any comments or suggestions, please do write them below, and I will see you next time. Okay, cheers, bye.